by using Euler's formula. So, as we all know, Euler's formula says that a cosine can be written as e to the minus of a complex exponential and then e to a plus for a complex exponential, and the a over 2 is the scaling factors you need to get it to work. Well, let's look at the Fourier series and consider what I call the symmetric terms. So here's the Fourier series, and I'm just writing it out. And I'm going to pick up the minus kth and the kth terms here and not worry about the other ones. So this is what I mean by symmetry. I'm picking up the terms where the harmonic numbers are negatives of each other. Well, notice that this looks a lot like that, and that looks a lot like that. So I think if we pick k equals to 1, I think we have found our Fourier series coefficients. All the rest of these are going to be 0 because we found how to express it, the sine wave, by this sum. And that's exactly what the answer is that the Fourier coefficients are all 0 except when k equals 1, and we get these quantities for the harmonic fundamental frequency and its negative counterpart. This is another interesting fact in that we've seen this already, that to express a signal as real valued, we need a negative frequency term and a positive frequency term. And we're going to see that their Fourier coefficients are related to each other in a very simple way, which we'll get to in just a second. But I want to go on to a square wave example now, where we're going to have to do the integral to see what we get. So here's our square wave, and you note that it's a discontinuous function. In fact, I didn't even define what it was at the point of discontinuity. We'll see that's an interesting point in just a second. And it turns out in order to do the integral, we're going to need to express it mathematically. So this is a mathematical expression for it. I notice I'm leaving open what it is at t over 2. Okay, so to do the integral, what we have to do is split the range of integration up so that within each range we have an analytic formula for what the signal is. So from 0 to t over 2, it was just a. From t over 2 to t, it's minus a. So now we can do the integrals, and these integrals are pretty easy to do. I'm going to do the one on the left. So we get 1 over t, and again we get a, and then we're going to get 1 over what that exponent is, j 2 pi k over t times e to the minus j 2 pi k t over t. And evaluate that from 0 to t over 2. Okay, at t over 2, the let's see, the t's cancel and that 2 cancels, and so what we're left with is e to the minus j pi k minus 1, because the exponential of 0 is 1. What is e to the j pi k? What is that equal to? It's equal to something very simple. In particular, I would point out that that's e to the minus j pi all to the k. That's the same thing. Well, in some quarters, this is considered one of the most interesting and important formulas in mathematics. E to the minus j pi, or even e to the plus j pi, is minus 1. So, what we get here is that this is minus 1 to the k. And then we bring on the minus 1. Turns out this other integral is the same thing. except with a minus sign, and because of the minus sign I had here, the two terms merge, and what we get is the following expression. So, the Fourier coefficient for a square wave is given by this, and when k is an odd number like 1, 3, etc., this is minus 1. You get minus 1, gives you a minus 2, and some things cancel, leaving you with this. Well, when k is even, well, that's 1, and 1 minus 1 is 0, so you always get a 0 here. So, the result is that the spectrum, the Fourier coefficients of a square wave only consist of odd harmonic terms. And furthermore, their harmonics are decaying as 1 over k. As the harmonic number gets bigger and bigger, the coefficient amplitude gets smaller and smaller. Smaller and smaller. So let's plot it. Let's see what it looks like. So here's our Fourier coefficient formula, and here I'm plotting the spectrum of a square. I'm plotting the magnitude in phase of the Fourier coefficient. This should remind you of what we did for transfer functions, where we plotted the magnitude in phase of the transfer function. And so I really am thinking about this Fourier coefficient, though, is a function of frequency, just like I thought about the transfer function as a function of frequency. And I'll re-express this axis in frequency in just a second. So the magnitude, you can see how the coefficients go down like 1 over k when they're odd, and when they're even you get 0, which is what the expression says. So this is the odd harmonic structure, if you will, of the superposition of complex exponentials that express a square wave. The phase is interesting. Again, we have something in Cartesian form. So what's the phase of that? Well, we need to know the phase of 1 over j, and there are lots of ways of thinking about that. That's equal to 1 over e to the plus j pi over 2, and so when that goes upstairs, you get e to the minus j pi over 2, so the phase is minus pi over 2. Okay, and since that term is the same for all of them, the phase is a constant at the odd harmonic terms, and it's 0 everywhere else, because the phase is not even defined. When the magnitude is 0, you might as well call it 0. So that's the spectrum, and a spectrum is a function of frequency. And all I've done here is relabel the axis to express exactly what is the spectrum is a function of f. This is in hertz. Okay, so it consists of something at a complex exponential at 1 over t, 3 over t, 5 over t, etc. So if the period was 1 millisecond, that'd make the fundamental frequency 1 kilohertz. So a square wave that has a period of 1 millisecond has Fourier series coefficients, has a spectrum at a kilohertz, 3 kilohertz, 5 kilohertz, etc. And the amplitude is going down like 1 over the harmonic numbers. That expresses the superposition of complex exponentials that we need to produce a square wave. Very interesting. And now let's do another example. That's a little bit easier to do, but this is a very important example, it turns out, just a little bit later in this course. So it's the periodic pulse sequence. So here's our well-known pulse, has a duration of delta, and I'm going to repeat it every capital T to make what's called a periodic pulse train. So again, I need a formula for it over the period, and here's our formula for the pulse, which I think is pretty straightforward. And doing the integral is very straightforward. You just plug it in, and you get the following answer.